Large hydro sites are all developed. I consider here the sites having capacity more than 10 megawatt as large hydro. Out of these, almost all the sites are developed. If you take the remaining sites, Moragahakanda, Broadlands and Umaoya, the construction has started at different stages. Morogolla, another power plant possible in the Mahali complex. Professor Wijetunga mentioned yesterday that the loan agreement is being signed now or was signed during the week. There is another project, Ginganga, having 49 megawatts. And once we develop all these, all the large sites are done for Sri Lanka. But still we have mini hydro potential for around 200 megawatts. We already have 220 megawatts. There may be potential for another, this is a very optimistic estimate of 200 megawatts. What can we do more? We can also optimize the operation of existing power plants. By doing that, we can get 1 to 3% more energy from the existing power plants. So that will be maybe 100 to 200 gigawatt hours in a year. How can we do that? Let me take the example of a Francis turbine. Most of our large hydro power plant, other than old Laksapana, are using Francis turbines. Now, on the picture you see a small mini hydro power plant using a Francis turbine. Francis turbine, unlike Pelton wheels and Kaplan turbines, have the undesirable behavior that its efficiency curve is not a flat one. So you get a maximum at about 80% discharge, and which is almost 92% or little more. But if the discharge reduces to 30%, the efficiency drops to 65%. So you need more water to get a kilowatt hour if you are operating somewhere here. Mini hydro plants do not have the option because they don't have a reservoir, so they have to depend on the amount of water available at the time, and the operating point is decided by that. But in the plants where we have reservoirs, we have a flexibility to operate at better points and get more energy from the same water. The operating point, the optimum operating point of a turbine and the system depends on design parameters like hydraulic design, inlet and outlet arrangements. But even for the same design, there can be manufacturing tolerances. If you produce two units using the same design, they are not identical behavior. The best operating point can differ from each other. But during the operation also, the wear and tear are different for equal machines. And the erosion caused by cavitation and silt can change from machine to machine. And the differences occur during repairs. When you do the repairs, probably a repair undertaken by one machine is different from the other one. So even if you have identical machines in the power plant, in the same power plant, the best operating points for these machines need not coincide. Now, then there is optimization problem. Let me take this 3-plant example from a US publication. Now, in the x-axis we have total flow, and there are 3 identical machines. And what are the options to keep the flow constant and get the best output? Now, somewhere here, there are 3 possibilities because one unit running, so you have 3 units, so you have 3 options for the same flow to get the energy output. So you see there's a wide variation there, leaving room for optimization. Then in the middle, that is the 2-unit operation, somewhere here. If you have 3 machines, there are 3 possibilities to select 2 machines, and there also there is a margin. For the same flow, you can get different values of output and room for optimization. When you run all 3 machines, then the margin is narrower, but still the solution is not unique. I have taken Canyon Power Plant as the case study for this. Canyon is one of the power plants in Laksapana complex where we have around 7 power plants in operation, 13 turbines are there. The Broadland power plant is under construction. Without that, we have 7 power plants. You can see 2 cascades. And other than in old Laksapana, everywhere we are using Francis type turbines, a runner of which is shown in the picture. Now, the Canyon power plant has a special feature. That is, the mouth of the tunnel is not starting from the reservoir in the Canyon power plant. So, the reservoir and the mouth of the tunnel is connected by a tube, a penstock-like tube, which is around 15 meters long. And there is another special situation. Canyon Power Station at the original design was designed for one single unit of 30 megawatts. But it was the latest construction done in Laksapana complex, and later in 1980s, original design was done in 1950s concept. In 1980s, they identified it is better to put 2 units each of 30. So, some of the original designs were changed, but not all. The tunnel was enlarged, tunnel cross section was increased, but this component was not changed. So now, the water required for both penstocks at Canyon Power Plant is to be taken by one single tube of the same size as one of these penstocks there for a stretch of around 12 meters. So that causes severe head losses. And unfortunately, the plant can't take the full capacity due to this restriction. Of course, it is designed to take 60 megawatts. The maximum it can take is around 50 megawatts because there is a severe head loss here. And actually, there is another thing that happens when the discharge is heavy. The head losses are so large. Sometimes a vacuum is created in the top part of this tube. And hydropower plants have the mechanism to safeguard from such a vacuum because these tubes can take pressure from inside, but they are not designed to take pressure from outside. If a vacuum creates, these thick penstock tend to distort. So, to avoid that, we have anti-vacuum valves. 2 of them are positioned here, and if there is a vacuum created, these valves open and safeguard the plant. And this has happened once in Canyon Power Plant. Due to that, that is one reason more not to take 60 megawatts. Now we face the optimization problem to minimize the amount of water used to generate a specified amount of megawatts from the Canyon, New Laksapana and Samanala cascade. There are 3 power plants in cascade. Constraints are there. Ponds should not spill and should have sufficient storage prior to the peak. Spinning reserve requirements should be maintained. In the optimization, we take all possible options, deciding on a resolution which you like. Say you can take 0.5 megawatt resolution and evaluate the water usage for each of the combinations, and that way you can select the optimum. The results. This optimization algorithm was run for one whole day without changing the total energy output, but evaluating the different water requirements. And water drawn from the Castle reservoir was not changed, but through the optimization we can reduce the water usage coming from Mausa-Calais by 4.1% within a day. Okay, the percentage is applicable for everywhere. And this water can be used again to generate electricity. Of course, this water will go through all 3 power plants and in future through broadlands and generate more energy. So that way, we are in a position to get more electricity from the same amount of water by doing this. Just to conclude, the potential to generate more energy from the existing hydropower plants by running them at most efficient operating point is there and not properly utilized up to now, unfortunately. Sample calculations done for Canyon show that savings can be as high as 4.1%. I have to mention that Canyon power plant is a special case where the saving potential is higher than average. If you go to some other power plant, we will not be able to achieve the same percentage of 4.1. A conservative estimate would give that we are in a position to save somewhere between 1 to 3% considering all the power plants in Sri Lanka, hydropower plants, which will give us maybe 100 gigawatt hours in addition. That is like a virtual power plant. So we are using the existing hardware, existing infrastructure and generate more energy using the same water by optimizing the operating point. Thank you very much.
Thank you, Professor Perera.